Hello student friends. So in today's session we'll learn what is Vander Waals equation, and in Vander Waals equation how pressure correction was incorporated, how volume correction was incorporated, right, for real gases. We know that real gases behave differently than ideal gases. So, right, Vander Waal developed a new equation for real gases which is known as Vander Waals equation. So, go ahead and learn well. Vander Waals equation. As real gases were quite different than ideal gases, they were not obeying ideal gas equation PV equal to nRT. So, Mr. Vander Waal, who won Nobel Prize for Physics in 1910, developed a correction in ideal gas equation which now is popularly known as Vander Waals equation, where there were corrections done to ideal gas equation in terms of pressure and in terms of volume, and that is now popularly known as Vander Waals equation, or it is also known as real gas equation, where A and B are Vander Waals constant and they depend on nature of gas. Mr. Vander Waal, a Dutch scientist, made corrections in volume and also did correction in pressure as per real gas. What are those corrections in volume as well as pressure? We'll see that part. First part, volume correction. If you check at very low pressure, now for an ideal gas, whatever is a volume of container. Remember, in PV is equal to nRT, V is a volume of container for an ideal gas. Now at low pressure, actual volume occupied by gas molecule is very small at low pressure. If you count all the space occupied by the gas molecules and you count that space of all the gas molecules, then it is found to be very negligible. At high pressure, same volume does not remain negligible. Just to understand this mathematically, at 1 atmosphere pressure, volume of the gas is 22,400. If all the molecules are brought closer enough and you find out their volume, then that volume is 32 centimeter cube. So if you check this volume as compared to 22400, then this value is definitely negligible. But instead of 1 atmosphere pressure, if you increase the pressure to 100 atmosphere, so you have increased pressure 100 times, then volume will become 224 centimeter cube. Then volume occupied by all the molecules is 32. Then volume available for free movement of molecules is volume of the container or volume of the gas minus volume occupied by compactly arranged molecules, and you will find that 32 is now not negligible as compared to 224. So what is the conclusion that we are trying to say? At high pressure or a moderate pressure, compactly present molecules occupy a certain volume. So volume of real gas is not volume of container. That's one. Then what is the volume of real gas? Science asks. It says its volume of container. Volume of a real gas is volume available for free movement of molecules. Remember that. That's volume of container minus volume occupied by compactly present molecules. Compactly present molecules. Compactly present molecules. So it is different than the volume of container. Remember, real volume is less than the volume of container. Just to understand this, we'll see from different perspective. Right, there is another perspective that we like to understand. Right, in this first diagram, you are able to see a dance floor has been shown. So this is a space available for a person to dance. That is for free movement. Now imagine one person is standing in the diagram number 2. Then what is the space available? Is it the same space as that of the dance floor, or the space has become lesser? Naturally, when the person is standing, the space available for him to dance will be the space on the dance floor minus the space on which he is standing. Same logic we are trying to say for real gas here. So volume available for real gas molecules to move is actually volume of container minus volume occupied by compactly arranged molecules. So the dance floor example tells you that. Still more for us to understand is, imagine this is a container, then these are the molecules which are present. Now imagine all these molecules are brought closer. Then this is what is a space occupied by all the molecules. Then what is the space available for the free movement? The space available for the free movement will be volume of container minus the space. Are you understanding it? Volume of container minus the space. So volume available for free movement of molecules is how much? Is V, which is volume of container, minus NB. Right, we consider that volume occupied by 1 mole of tightly fitted molecules is B. 1 mole occupies B space. So N moles will occupy how much space? It will be NB. So tightly fitted N moles of gas will occupy NB. Now it has been found scientifically B is not the actual volume of all the gas molecules. It is 4 times the actual molecules of the gas. What does that mean? The science says, right, if you make all the molecules come very close, as in this diagram, you cannot bring the molecules edge to edge closer. This cannot be possible. You can bring them enough close that they should not have repulsive force. So this is actual right space occupied by the gas molecules. If you put them edge to edge, but in reality they don't exist like this, they exist like this. So what we are saying is this is B and this is Vm. So if this is Vm, then molecules which are arranged compactly without repulsive forces is B, that is 4 times Vm. Now, so Vm is volume occupied by 1 mole of tightly fitted molecules with no intermolecular forces, or neglecting repulsive forces also. That means you are keeping them edge to edge like this. But for all practical purpose, B is volume occupied by also 1 mole of a solid. Even solid will try to arrange like this, not like this, because in solid also repulsive forces will be avoided. So you can remember B can be considered volume occupied by N mole, right? 1 mole of a solid, 1 mole of solid, and NB is volume occupied by N moles of solid. You can take like that. So what is the correct volume of a real gas? Conclusion, right, real volume of a gas is V real is volume of container minus NB. So this is what is the correction. So correction of volume is this. What is the pressure correction? To understand pressure correction, then if you consider any molecule like this molecule, if you consider, then can I say this molecules will have intermolecular forces from all the sides? Will have intermolecular forces from all the sides and they will cancel each other, and such a molecule will have free movement. But if you compare a molecule which is closer to the wall, then that molecule is having intermolecular forces which are unbalanced. So this molecule we are talking about, this molecule which I am shading it out. Okay, so this molecule which I have shaded it out is closer to the wall and it has intermolecular from this side. So because there are attractive forces, the force which this molecule will go hit the wall will be lesser. So if you check, when a molecule is about to strike the wall of the container, it experiences a force of attraction towards other molecules, and therefore force exerted on the wall will be lesser, therefore pressure exerted will be lesser. That means we are saying in real gas, pressure exerted will be lesser than in ideal gas. Why? Because in ideal gases, there will be no intermolecular forces. So the same molecule will go and hit the wall with larger force. If larger force, larger pressure. So who has more pressure? Ideal gas or real gas? Ideal gas. So what is the pressure of a real gas? Pressure of a real gas is pressure of ideal gas minus some factor. What is that factor? P dash or P hyphen is pressure lessened due to intermolecular forces present in real gases. So if you say from ideal gas perspective, what is the pressure from ideal gas perspective? It's a real gas pressure plus that factor. So that's a pressure correction. So pressure correction. So if you check, ideal gas equation is equal to PV is equal to nRT. That's the ideal gas equation. And P ideal is P real plus that factor. And V ideal, that's Y, right? V ideal means volume available for free movement of the molecules. How much is the volume available? It is volume of container minus NB. So pressure factor is real pressure plus an extra factor. So Mr. Vander Waal found out that the extra factor which was to be added to a real pressure was AN square by V square, and the volume is V minus NB. So that is what is a correction, and such a equation is now popularly known as Vander Waals equation. So Vander Waals equation is the changes that we have done it to ideal gas equation by bringing in the pressure correction and the volume correction. So that was for you to understand, right, all about Vander Waals equation logic, how it was developed from an ideal gas equation. We don't have derivation for this part and we don't have derivation for this part.